Okay, so you got your test back. And Emily, that's so incredible. They marked them all. I know, right? What can I say? Well, I cheated on the assignment. So what you'll see is the assignments are just stapled to your test. They're just in the back. What I did, if there's a check mark, you just got a completion mark. So if you handed it in, you got 100%. Just because I marked the test and the assignment was basically the same, so, and worth way less. So I'm not going to waste my time doing that. So I'm going to try to get them back to you guys. So congratulations on your 100% assignments. So let me just, that's why I'm just kind of kill myself getting ready for today. And then now I'm here and now I'm like, I'm so tired. So tired. I'm done with this week already. So we've got chapter 4 notes. I posted them on the Null chat. Printouts. So many printouts. Maybe it's the snow, maybe it's coming up on reading break, but I just haven't had that big a turnout today. Post-test, everyone's kind of taking it easy. Let's see here. Okay. So, just a note. What? Sorry about that. Can you guys see okay anyways? You have it, but it's harder to see. So, assignment 3. Is stapled to your test. For completion marks only. Sometimes I cheat like that. Definitely, because I was kind of fire drill marking these things, maybe check up my adding. So how I mark is I just subtract marks as I go, right? So you'll start with 100% and then I take away marks. That way there's like some secret marks that everyone just kind of has. I think it's a nicer way of marking than you having to build up to 100%. So you'll start at 100% and then I bring you down, or you bring yourself down. I'll say that. Remove all responsibility from me. Not entirely. So just check up my adding, and if you have any questions about the marking, then just let me know. I'll post the solutions. I haven't yet, but I'll post the solutions. There's 2 versions. For the first test, I keep it on the down low. So special instructions, if there's a colon after, your version 1, and if there's no colon after, your version 2. So that'll say on the solution, so you'll know which one to look for. But just check the adding. and subtracting, I guess, on test number 1. Overall, I thought it was a really good test for you guys. So one thing I will say is that test 2 doesn't have any multiple choice. Some people, when I say I do multiple choice on the first one, just because there's so many kind of theory things that we have to test. And they're like, oh, multiple guess, huh? And I'm like, well, multiple choice is actually really difficult to do. And so like as a student, it's really hard to do well on multiple choice. So on test 2, there's no multiple choice, but there is multiple choice on the final. I know, womp womp, yeah. I want to say 70, I think it was, let me just see here. I feel like it was 39. No, that can't be right. I'm trying to remember what that number was. Anyways, I can check for next time, but it was around 70, 75, 70-ish. In the 70s, how about? Vague enough? So obviously, if you should have a lower mark than I gave you, then don't tell me. Just start the car. Okay, so that's that. I gave you your chapter 4 notes. Okay, great. I've been lugging around all these notes. I've got printouts from chapter 2 and chapter 3. So if you are missing some of those, then just let me know. I always bring them. No one wants them. That's okay. Yeah. It's cumulative, yeah. Yeah, I know. But for a little while now, we'll leave kind of test 1 stuff in the dust, and we'll start chapter 4. So chapter 4 is kind of, well, now we're getting into my favorite part of this course. So the beginning stuff, it's like, oh yeah, terminology, things we need to know, whatever. Not whatever, kind of whatever. But now we get into inference. Okay, so we said at the beginning of the course, the whole idea of statistics and the reason you have to take this course is because we want to be able to take some sample, right? Take information from a sample to be able to say something about the whole population, right? So that's the whole idea of statistics. And so what we could say is we could say, well, we want to take a sample to infer something about the population. And that's where inference comes from. Okay. Let's make a little note about that here. When we take information from a sample, to infer something about the population. So far, we've only talked about a single observation, right? So the speed of a manatee follows a normal distribution with a mean this and a standard deviation that, right? So we've been talking about a single observation. And so here, when we're talking about, okay, we take information from a sample, we're not just gonna take one individual to try to say something about the whole population, right? We're gonna take the average or the mean of a sample to try to figure out what the population mean might be, right? And so now we're kind of changing gears, and now we're gonna start talking about the distribution of the sample mean. And so we'll start here. And say that, okay, well, we know this notation. Right, we're comfortable with this notation now. If x, so a single observation x, follows a normal distribution with a mean mu and a standard deviation sigma, then the sample mean from that group, right, a sample of size n from this group, the sample mean will follow a normal distribution with a mean mu and a standard deviation of sigma over root n. Right? So the mu stays the same, but the standard deviation of x bar, right, of the sample mean, becomes the standard deviation of a single observation over the square root of n. You can see how that gets kind of muddled, right? And so what we call this chunk here, the sigma over root n, we call it the standard error. So the standard error is just the standard deviation of x bar. Okay. So let's make a note here. Sigma over root n. This is the standard error. I'll just put in brackets the standard deviation of x bar. This here, this whole thing, is the sampling distribution, right? Follows a normal distribution with a mean mu and a standard deviation sigma over root n. So that is a distribution. So this is the sampling distribution of x bar. So if we think about it, right, so we're sampling from a group that follows a normal distribution centered on the mean, right? It makes sense that our averages from this group would also be centered on that same mean, right? That's not that crazy, right? If we consider this room, the whole population, right? And we take our heights, for example, I take the average height of 10 people, right? Randomly select 10 people, calculate their average height, put them back in, take another sample of 10 people, calculate their average heights. Those averages, they're not going to be exactly the same as if we calculated everyone's, like we included everyone's height, right, to find the average, but they should be pretty close, right? And so this part's not that crazy, right? It stays centered on mu, and so that's okay. The sigma over root n comes from, okay, well, if we think about just this room as the population, right, makes it more manageable. Then if we talk about all our heights, right, we made a histogram of it, there would be a lot of spread. Not a lot, but you know, have the shortest person over here, the tallest person over here, right? And so be a lot of spread. Once we start collecting averages, right, those averages are going to be closer and closer, right, than single observations, right? And so here we're taking into account the sample size, because if you think about it, if I take a sample of size 10, I calculate their average, and then I take a sample of, I don't know how many people are in here, but let's take a sample of 20, might be almost all of us, right? Take a sample of 20, calculate that average is going to be closer to all of our averages, right, together. And so what happens is that as n increases, so as we increase our sample size and collect more and more of the population, right, the standard error is going to decrease. Right? The square root of n is going to increase, just not as quickly as n is increasing. And then we can divide sigma by that number, but that number is still increasing, right? So get smaller. And I've got that down here. So sigma over root n is the standard error, and we'll abbreviate it SC if we have to. And then as n increases, sigma over root n decreases. Okay. So all it's saying is that the variability of x bar, so the variability of a sample mean, sorry guys, is going to be a lot less than for a single observation. Okay. If you have a look at this, we could have started with this distribution, right? But it's a little bit much to handle, because this is just a special case of this. Right? If you think about a single observation, that's a sample size of 1. Right? The average of a sample of size 1 is just itself. Right? So that's fine. U stays the same, and then sigma is sigma. And if we have a sample size of 1 is just 1, the square root of 1 is 1, sigma divided by 1 is just sigma, right? So this is a special case of this one here. Let's do an example. The entrance exam for business schools, the GMAT, I guess you guys would know more about it than I do. Given to 100 students, had a mean of 520 and a standard deviation of 120. Okay, great. These first few questions are just really gonna kind of nail the whole point down. What is the sampling distribution of the mean x bar? So what we're gonna do, I'm gonna add a page here. Let's say example 1. First, I'm going to identify all the information that I've been given, right? And so we've got a sample size of 100, right? Because 100 students, with a mean of 520 and a standard deviation of 120. So the mu is 520 and the standard deviation is 120. Part A wants to know, what is the sampling distribution of the mean x bar? Okay, so the sampling distribution of the mean in general is x bar follows a normal distribution with a mean mu and a standard deviation sigma over root n. So that's the general form for answering this question. We know mu, we know sigma, and we know n. So now we can just plug those in. So we've got x bar follows a normal distribution with a mean of 520, a standard deviation of 120 over the square root of 100. I would probably just leave it like that, probably because I'm lazy. Or we could write x bar follows a normal distribution centered on 520 with a mean of 120 divided by, I guess, 10, 12. So if we think about sigma versus the standard error, right? Sigma is 120. And so that's for a single observation. Right? We're expecting a lot of spread here, but for a mean of size 100, or from size 100, we're expecting a spread of 12, right? Really condensed it. Any questions about that one? So B, what was the standard error for the mean of this sample of students? So the standard error is sigma over root n, which we just said was 120 over the square root of 100. We actually already calculated it to be 12. Okay. As the sample size increases, what happens to the standard error, assuming the standard deviation remains constant? We already said this, but as n increases, oops, assuming sigma remains constant, the standard error, sigma over root n, will decrease. So for the last part, this is the one that I kind of stole this problem for. If the sample size is doubled, what's the impact on the standard error? So if we let n be 200, right? It was 100, but now I'm making it be 200, so doubled. Find the standard error. So the standard error is sigma over root n, which is, what was it, 120 over the square root of 200. I get 8.48528137. Doubling n, shorthand for the sample size, results in a, let's do 12 minus 8 point whatever, in a roughly 3.5 unit decrease in the standard error, right? Because we went from 12 at a sample size of 100, and then when we went for 200, we've got a standard error of 8.48. Kind of quick and dirty math, 8.5. So doubling our sample size, just because of how square roots behave, right? Doubling our sample size doesn't cut our standard error in half, but it decreases it. Any questions about that one? Yeah. Unit. Let me give that one another go. Well, that's pretty good. I know. Get so sloppy on this thing. Don't worry, I'm sloppy in real life too. Any other questions? Decrease in the standard error. Okay. So, of course, I shouldn't say of course, but because we want to know something about the mean, right, and now we know that it follows a normal distribution, knowing that it follows a normal distribution means that we can calculate z-scores, right, and then use the z-table to find probabilities. Okay. So, just scroll down, next page. We can calculate probabilities associated with a mean observation, right? So I'll just make a note here, kind of up above here. So X bar, remember, follows a normal distribution with a mean mu and a standard deviation sigma over root n. And then from before, we said Z is X minus mu over sigma. That was when X followed a normal distribution centered on the mean and a standard deviation of sigma. So now, all we're doing is we're swapping out this X, right, for X bar. Mu stays the same, that's still the center. And then instead of sigma down here, we've got sigma over root n in the denominator. Right? So it's just how far is X bar from mu, taking into account the standard error. So once we can calculate a z-score, then we're back to what we know, right, from this test that we just did, the assignment, right? And so you know how to calculate a z-score, use the z-table to find probabilities, right? Probabilities are areas under the curve. So we know how to do all those things. Once we're here at a z, right, z behaves the same way as it did before. Right? It's just how we got it. So let's do example 2. Let me add a page here. Suppose the mean weight of boxes shipped by a company is 12 kilos with a standard deviation of 4 kilos. There's no mention of it follows a normal distribution, but that's okay. And I guess I shouldn't have thrown that. I should have said it follows a normal distribution here. But what we'll establish in a little bit is that it actually doesn't matter what population it came from. It will follow a normal distribution, which is kind of cool. So it has a mean of 12 and a standard deviation of 4. Boxes are shipped in pallets of 10 boxes. Okay, so each pallet has 10 boxes. And then the shipper has a limit of 150 kilos for such shipments. So part A, what's the probability that a pallet will exceed the limit of 150 kilos? So a probability is an area under the curve, right? And so we want to translate this to an area under the curve, right? A normal distribution. And because we know this normal distribution is centered on 12 with a standard deviation of 4, what we can do is we can actually take the 150 kilos, right? And that's the same as saying, well, what's the probability that the average weight, right, is more than 15? And so part A, it's kind of down here. Example, is it 2 or 3? 2? Thanks. So we've got mu of 12, a standard deviation of 4, and our sample size is 10, right? 10 pallets, or 10 boxes per pallet. So the situation that we have, right, is we have a normal distribution centered on 12 with a sigma of 4. So how we draw this curve doesn't change for means and for a single observation. It's just our calculation. And then we want to know, okay, well, if we've got 15 up here, what's the probability? So what's the area under the curve? What's the probability that the mean weight is more than 15? So we know how to do this for a single observation, and so we can just calculate our z-score. So z, just keeping in mind that now we're talking about the mean of 15, right? So x bar minus mu over sigma over root n. X bar is our 15, right? We want to know how far is 15 from 12. So 15 minus 12 over 4 divided by the square root of n, which is 10. Right? 10 boxes per pallet. 15 minus 12, that one's fine. 3 divided by, and then square root of 10. 1 over that times 4. Store that. 1.264911064. So 3 divided by that puts me at 2.371708245. Z has to have 2 decimal places, right? No more, no less. And so 2.37 is our Z. Now we have a Z, which we know what to do with, right? We can go to our Z table and find the area to the left. We want the area to the right. So then we're going to do 1 minus, got a positive Z here. So I'm just going to write out what I'm doing. So using the Z table, we find the area to the left, right? The table will only give you the area to the left, right? So we start there, and if you need the area to the right, then you make that an extra step. We find the area to the left of Z equal to 2.37 is, so 2.37, I get 0.9911. And if you don't have a copy of the tables, I've got some here. You need to borrow. So that's the area to the left. Right? Here, we want this area. And so we need 1 minus that. So the area to the right is 1 minus 0.9911. Bless you. Which is what? 1 minus 0.9911. Oops. 0.0089. So what does that mean? It means the probability here, the probability that a pallet will exceed the limit of 150 kilos, right, is the same as the average exceeding 15. So that probability is 0.0089. Therefore, the probability the shipment is overweight is 0.0089. Questions about that one? So really familiar from the test, right? Just changing it to talk about the mean instead of just 1x. Throw in another page here. Because I think that was just part A. Part B. What is the mean weight of the heaviest 10% of boxes? So the heaviest 10% of boxes, if we had to draw it out, it's still centered on 12, and sigma is still 4. And just in our calculations, we use sigma over root n. And so now we want to know, okay, the heaviest 10% of boxes, oops, that's not unknown. We're forcing that area to be 0.1. You've got two options. You could, because the next step, right, is to figure out, okay, well, what Z score corresponds with this value, right? The Z table only gives you the area to the left, right? So one thing you could do is just find the value closest to 0.9, or the table entry closest to 0.9. Right? Or if you wanted to, you could say, well, I'm going to look for the area closest to 0.1, realize that that's going to give me a negative Z, but what I'm actually looking for is the positive version of it. That's fine. So it just depends on what you want to look for. I'll stick to the 0.9. Not getting too crazy here. So here, this area is 0.90. So again, I'm just going to write out my work using the Z table. We find the table entry. Remember, the table entries are all these values in the body of the table, right? So those are your table entries. So we find the table entry closest to 0.90 is, we know it's going to be on the positive Z side because it's above the mean, right? Because it's greater than 0.5. So 0.90, scanning here. It's between 0.8997 and 0.9015. You can just use your calculator to figure out which one's closest. In my mind, when I look at 0.9015, I call it 15 away. That kind of makes sense. I don't know. That's how my mind works. You can do actual math if you want to. And then 0.9 minus 0.8997 is only 3 away, right? So that's the closest one. So is 0.8997. This value, right, can be traced back to a Z score, right, which corresponds to What does it correspond to? 1.28? Oh, should say Z of 1.28. So 1.28 is the standardized value of this point. Now we can unstandardize it to find the weight. Right? That makes that cutoff. So now we have Z is X bar minus mu over sigma over root n. Z is 1.28. We're trying to solve for X bar. Right? What mean weight cuts off the heaviest 10% of boxes. So X bar minus mu, which was 12, over sigma, which is 4 over the square root of 10. I cheated earlier and said X bar minus 12. I stored 4 over root 10, but it's 1.264911064 times that by 1.28, right, to bring it over to the other side. So we get 1.619086162 is X bar minus 12. Then add 12 to both sides, we get X bar is 13.619086616. Therefore, the mean weight of the heaviest 10% of boxes is more than, I'll do 13.62 kilos. Same procedure that we're used to, right? Just a slightly different Z formula, right? But the procedure is all the same. Any questions about that one? C. What mean weights capture the central 90% of boxes? So you've seen this question before, right? But now we're talking about the means. What means capture the central 90%? So you had to do this on the test or a version of it. So we've got this normal distribution centered on 12. And then here at some X lower or X bar lower and some X bar upper, we've got the central, what did I want, 0.9? I think, 90%. Cool. If I've got 0.9 in the center, right, and it has to be symmetric, so then I've got 0.1 left over, split evenly amongst the two tails, so 0.05 and 0.05. We use the trick, right, that if we found the Z for the X bar lower, right, that value, then we can just drop the negative and use that same Z score for the upper value, just because it has to, they have to be the same in order for it to be the central 90%. So we can say, using the Z table, we find the table entry, right? We're looking for the table entry closest to 0.05. So we find the table entry closest to 0.05 is, what is it? Oh, it's the one that's even Steven around 0.0505 and 0.0495, isn't it? I'll just confirm here, but I think so. There she be. Is either 0.0505 or 0.0495. If you've got a choice like this, you can just pick whichever one you want. I will use 0.0505. Why not? It's the first one. Which corresponds to Z equal to negative 1.64. No, it's really right. Yeah, I'll show that little sneak attack in a little bit here, but it's good. It's good. Yeah, if you find yourself kind of split evenly amongst the two, then go ahead, take the average if you want, or I'll show you a little trick in a little bit. Oh, what a cliffhanger. I know. It's all I can muster today. Cliffhanger. So, which corresponds to a Z of negative 1.64. Okay. I'll just keep going here, which is the standardized value, just because I need to differentiate between the X bar upper and X bar lower, or other way around, right? And so, which is the standardized value for X bar lower. And then I'll just say by symmetry, Z equal to positive 1.64 is the standardized value for X bar up. So you've got a couple of options that I just want to run you through, right? You could just go ahead and say, well, I'm even between these two, so I'm just going to take the midpoint. That's fine. That's great. Or if we venture into table C, which we haven't looked at before, and so I'll just kind of grab it here. Table C, or the T table, we haven't calculated T's, but spoiler alert, T's behave very similarly to Z's, right? So it's not going to be that big of a transition, but what we have is the T table gives us these confidence levels up at the top, okay? And so these are just symmetric confidence levels around the mean. And then if you scroll down to the bottom, go up a little bit. Okay. You've got Z star at the bottom. So you can ignore everything else for a little bit, right, for another couple of classes or so. Right? You can ignore everything except for this Z star line, because it's just going to be a little bit easier. So if we want the central 90%, that's the confidence level of 90%. So then if you go down, 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 the Z that you would use is 1.645. So same idea. You have a 95% confidence level, sorry. So the central 95%. Key is that it has to be the central blank percent. Right? So if you want the central 95%, then you can roll down here. You'd use a Z of negative 1.96 and positive 1.96. So that's just another way that you could do it. Wait, what the? Weird. Okay, so I'll just write here, or, and we'll talk more about using the t-table to find those values, but I'll just introduce it here because that is what we're doing, right? We're using these values. So, or using the t-table, or what I'll say first is using table C, and then in brackets the t-table. Using table C with a confidence level of 90%, we find Z star is 1.645. I'll just leave it at that because for this example, I'm just going to use the 1.64 that I decided on earlier. Right? But if you wanted to use 1.65 or 1.645, all of those are all valid. For this example, I will use Z equal to plus minus 1.64. So we've got Z as X bar. Let's start with the lower, right? Because the whole goal of this operation was to find the Z scores and then unstandardize them to find the X bar lower and X bar upper for the central 90% of the weights. So X bar lower minus mu over sigma over root n. Oops. So for X bar lower, we've got a Z of negative 1.64 is X bar lower minus mu, which is 12 over 4 over the square root of 10. Cheating a little bit because I've got 4 over root 10 in here already. So call 1 times negative plus 12. Skipping straight to the goods. X bar lower is 9.925545855. Doing the same thing for X bar upper. Oops. X bar upper minus mu over sigma over root n. I've got 1.64 is X bar upper minus 12 over 4 over root 10. X bar upper times minus 1.64 plus 12. 14.07445415. Therefore, the central 90% of mean weights is between, let's say, 9.93 kilos and 14.07 kilos. Hopefully that was the end of the example. Otherwise, I should have added a page. Phew. Any questions about that one? Okay. So, I foreshadowed already, okay? But the central limit theorem is just as important as it sounds. The central limit theorem is really important because what it says is that, yeah, if we're sampling from a normal distribution, then the averages, yeah, they'll follow a normal distribution as well. That's kind of, yeah, fair enough, right? But the central limit theorem says that regardless of what distribution you're sampling from, so even if it's really skewed, this distribution that you're sampling from, if you're looking at averages from that group, those averages will still follow a normal distribution. So that's pretty cool. So the only kind of hitch is that our sample size has to be large enough, right? And it's really hard to kind of decide, well, how large is large enough? So it kind of depends on a few things. So it depends on, well, how close to the normal distribution do you need to be, right? Then you have to increase your sample size if you need to be really, really close to the normal distribution. Or it depends on the distribution that you're sampling from, right? If you're sampling from something that looks approximately normal, then you don't need a huge sample size to get a normal distribution out of your mean. Whereas if you're sampling out of a really skewed distribution, right, then you'll need to increase your sample size to try to adjust for that. The great debate, how large is large enough? So in practice, some statisticians say a sample size of 30 is large enough. And we'll just kind of use that as a baseline. I've read papers where 15 is large enough. I'm kind of like, not really. At the end of the day, it's just what sample size do you have? That's all you'll have, right? And so there's nothing you can do about it. Others recommend a sample size of at least 40. And so, again, it depends on the population that you're sampling from. Okay? Thinking about a lot of money things, right? If you're talking about the average income or something like that, because income is really skewed often, right, you'll want to have a large sample size, right? Because you're pulling from the skewed distribution, and so to adjust for that, you want to have a large sample size so that the mean that you're calculating will follow a normal distribution. And this, I've got this illustration here. It's really kind of just for fun and to illustrate the point. Oh, we wrote a lot, didn't we? Okay. So I generated this distribution, 1,000 points. It's from a beta distribution, so it is skewed, right? So because we've got 1,000 points here, and it still looks like this, yeah, we can say it's skewed. And so what we're going to do is we're going to pretend that this is our population. Right? And so what we're going to do to see how the mean is going to behave and how it eventually stabilizes as we increase our sample size is we're just going to pull a sample size of 1, calculate the mean of it, that's just itself. Turns out that that was way up here. Let's pretend. It's a little zoomed in, so we don't know if this is the starting point, but let's pretend. Okay. So first point we pulled looks like it was around 0.85. Fair enough. So then we go back in and we pull out another point. Now we've got a sample size of 2. Right? Now we calculate the average of these 2 points. Okay. Bounce this down here. Right? And we go and we pull out a 3rd point. Now we calculate the average again with 3 points. Bumps us up a little bit. And so we get this kind of movement as we keep increasing our sample size by 1. And so even though we're pulling from this really skewed distribution, right? Once we hit a sample size of, I don't know, even 200, it starts to kind of hang out. So this dotted line is the population mean, right? So that's where it should be stabilizing to. And so even at a sample size of 200-ish from this skewed distribution, the mean starts to kind of hang out where it should be. Right? Over here, yeah, we're jumping around and there's a lot of variability. Right? But as we increase our sample size, that sample mean is going to get closer and closer to the actual mean. Okay. Questions about that? Oh. So there's a few things that we need to kind of check to make sure that the central limit theorem applies. And so the first thing is that the observations are independent. And if you've taken a random sample, then yeah, you can assume that you have independent observations. The sample size is large and greater than 30 is a good rule of thumb, but we will be a little bit flexible on that. And then, of course, the population distribution is not strongly skewed. Unless you have a huge sample size, then it doesn't matter. Any questions? Okay. So I'll just start talking about hypothesis testing because it's kind of I'd say it's the best part of the course. And what's fun about it is, well, it's not fun in the beginning because there's a lot of rules and a lot of things that we need to keep track of, a lot of ins and outs of hypothesis testing. But what's really nice is that once we've got those under control, which is what we'll do here in chapter 4, is we'll kind of lay out all the rules. Then all of those apply to all the next chapters that we'll be doing. Okay, we'll be doing hypothesis testing for all these different types of questions, right? Because how you've collected your data is going to dictate, okay, well, how do I want to analyze this, right? And what your research question is going to dictate, well, how should I analyze this appropriately, right? And so there's lots of different hypothesis tests, but hypothesis testing in general, you're going to follow the same steps every time. And so we'll talk about those in this chapter, but then we'll have those tools going forward. Same thing for confidence intervals. So the 2 main things in inference that we'll be doing is hypothesis testing, that's a big one, and confidence intervals. So hypothesis testing, can zoom in a bit, is pretty much, yeah, the reason you have to take this course. So it's the moneymaker of statistics. So whenever you want to be able to say that this is significantly different from this, right? Whatever those 2 things are, right? In my little example here, I've developed, let's say, a painkiller, right? And I want to be able to say that my painkiller acts significantly faster than any other painkiller, right, then what I have to do, right, is I have to collect a sample of how fast my painkiller acts, right, compare it to how fast other painkillers act, and then I can use hypothesis testing to prove that mine acts faster, significantly faster than the other painkillers. And so this significantly, right, statistically significant, gets thrown around a lot. Right? There's a lot of work that gets put into being able to say statistically significant, and that's what hypothesis testing is going to be all about. So we'll just talk about, there's going to be 4 steps, and the 4 steps that we follow, and then I think I'll give my throat a break. But first thing we're going to do is we're going to state the null and alternative hypothesis. And so I remember, I think science 9, I don't know, whatever. Maybe it was elementary school, who knows, it's all a blur. But you've got some hypothesis, right? That's science. I boil water, it turns into gas, freeze water, right? And so you've got this hypothesis or theory. And so we've got the same situation here, but we just need to be able to communicate it symbolically. Right? And so that's what your null and alternative hypotheses are. Right? I'm going to assume that my drug is the same as all the other drugs until I have proof otherwise. Right? That's going to be my null and my alternative hypothesis. And step 2, I just call it do the test. Right? The doing the test is actually something that we know how to do already. Doing the test is, well, to start off with, it'll be calculating a z-score. So it'll be just calculate z is x bar minus mu over sigma over root m. It'll be as simple as that. Later, it'll be calculating a t, but the idea stays the same, right? So the step here, we're just calculating how far is x bar, our sample mean, from our hypothesized mean, right? I got a sample mean of 4, right? Is that significantly different from 5, let's say? It's different from 5, it's not the same as 5, but there's kind of some wiggle room, right? And so here we're able to establish if it's significantly different from 5. Find the p-value is also something that I've been making you do already. The p-value is find the area in the tail. Okay? So if you got a negative z, it's the negative tail. If you got a positive z, it's a positive tail. Right? So steps 2 and 3, we've been practicing already. Right? And we kind of know those and are familiar with those. And so here, this is find the area in the tail. And then we're going to draw our conclusion. Our conclusion is going to have 3 parts. And one, we're going to talk about, okay, well, the p-value, the area in the tail, right, that's going to help us decide whether we can reject the null hypothesis or not. And then, of course, what does that mean in terms of the question? And so there are a lot of ins and outs. And so what I want you to do over reading break is just read, I don't know, it's only like 4 more pages. You can do it. Just have a read through this. Of course, we'll go through it, but it'd be really good if you just had a quick overview, right? So what I do now in each of these subsections is I just go through, okay, well, what does it mean to state the null and alternative hypothesis, right? And what are the ins and outs of that? And then what does it mean to do the test, find the p-value, draw your conclusion, okay? Any questions, comments, concerns? No? All right. Have a good break, you guys. I'll see you on the other side. Sure. So